Here we go. So partial fraction decomposition. So the rules of partial fractions is any polynomial can be factored into linear and irreducible quadratic parts. If it's a linear part, then we just need a whole number or some kind of number in the numerator. If it's a quadratic part, then we need a linear function in the top, is what the way it works. Okay. So the numerator is always going to be 1 degree smaller than the denominator, depending on what we started with. If you have a repeated factor, like in this case right here, my denominator is x cubed plus 4x squared. That factors as x squared times x plus 4, right? Mm-hmm. Now, x squared is really x times x. So I have 3 linear factors here. The x is a repeated linear factor. So if you think back to your college algebra days, you looked at the multiplicity of a root, and that talked about how the root went through or bounced off of the x-axis. So here, my linear factor of x has multiplicity of 2. So that means in its partial fraction decomposition, it's going to have to come up more than once. So for the decomposition here, they're basically telling me how it's going to break down. So they're saying that my original fraction of x squared plus 49 divided by x cubed plus 4x squared, because of the way the denominator factors, will end up looking like this. Some number above x. Why some number above x? Because 1 degree less than x is x to the 0, which means it's a constant. Now, repeated factors, like the x squared, they still get just a constant factor, not a linear factor at the top, because of the repetition. And then there's going to be some number c over x plus 4. Why just some number c? Because x plus 4 is linear. 1 less than being linear is being constant. Now my trick is to do some clever math and come up with an a, b, and c. So the clever math that has to happen next is eliminating denominators by multiplying through by the lowest common denominator, which is the original denominator. And when you do that, a whole bunch of stuff cancels. Right? So, new page. So I'm stuck with, where'd it go? X squared plus 49 on this side. Oops. And then I had an a over x over here, but I'm about to multiply it by that, which means one of these x's is going to cancel, leaving the other 2 factors. So I'm going to have a times x plus 4. Then I'm going to have a b term. When I multiply this denominator by the b term has an x squared in the bottom. So both of those x's cancel, leaving me just an x plus 4 times b. Room. Time. And then finally, I'm going to get the c term. And what happens with the c term? It had an x plus 4 on the bottom, which gets canceled, leaving what behind? X squared. Okay. Yeah, so we eliminate the denominator. So I mentioned before that this section pretty much takes like 60% of what you learned in college algebra and applies it to a single problem. So now we pick clever values for x to try and find a, b, and c. What's a clever value for x here? -4. -4 is a good one. 0 is another good one. Okay. 0 is my favorite. I'm going to do that one. So in your notes, when you do this, I highly recommend you write down what your clever value is, and then you write what happens with that clever value. So when I plug in x equals 0 there, I'm going to get 0 plus 49, which is 49, equals, well, the a term is gone now, right? Because it has a factor of x in it. X is now 0. The b term is not gone. What's going to happen there? 0 plus 4 is 4, so I get 4b. And what happens to the c term? It's gone because I plugged in a 0 right there. So c is gone. Cool. I know now that b is 4 over 49.
Wait, wouldn't it be 49 over 4?
Yeah.
Did I do it backwards?
Yeah.
Oh shit. Thank you. Yes, it would be 49 over 4. Okay, the next clever value for x that was suggested was -4. And so if we plug in -4, what goes away? Let's see, the a term goes away, right? Because -4 plus 4 is 0, right? So the clever values are numbers that make stuff disappear, become 0. B, do we have a b term? Oh, I forgot to do this side. Let's see. -4 squared is 16. 16 plus 49 is 63.
Sure.
No, it's not. It's 64, isn't it? Yeah, that one. 65. All right, so A is gone, B is gone. -4 squared is 16, so I get 16C. This is working out pretty good. So C is 65 over 16. Out of clever values. Darn. Yes?
B and C and use.
Yeah, you can pick any value you want now. So 1 is a nice value. And I know B and C, so I can solve this. So if I plug in x equals 1, and I know the values of B and C, I can now find A. So let's see, 1 squared is 1, plus 49 is 50, equals, let's see, 1 times 5 is 5, so I get 5A, plus B is 49/4, and 1 plus 4 is 5. And C is 65/16. And I'm plugging in 1. 1 squared is 1. So now we just have to solve that for A. So do some math, find out A for me. So A is whatever that is. Let's see. So I'm quick on the draw with Desmos. It's going to be 160 minus 196 minus 13 over 16.
I got -23 over 16.
That's right. Anyone else?
What did you get? -23 over 16.
That's, what do I get? I've got 160 minus 196 minus 13. I got -49.
That's what I got.
Maybe I did.
Yeah. Could have made a mistake, but two other
Yeah, that's
people
what I got.
Yeah, so it looks like it's -49 over 16. All right, so now we have values for A, B, and C. And that came off. So the point of this is that integrating x squared plus 49 over x cubed plus 4x squared is going to give you the same answer as integrating. Let's see, that was the one we just calculated. Negative 49 over 16 over x. And then b was what? 49 over 4. 49 over 4 over x. Maybe I should just write this as one big one. Back up. I need a big eraser apparently. Come on. All right, so then I have plus 49 over 16 over x squared. And then what was it? 65 over. Oh, that were 65 over 16. 65 over 10. 65 over 16. X plus 4 dx. And each of these actually isn't too bad. This is just a constant, so the antiderivative is going to be negative 49 over 16. What's the antiderivative for 1 over x?
X squared over 2. Or, ln x.
ln x
It's like,
plus 49 over 16. Antiderivative for x to the negative second power.
Negative.
X to the negative x to the negative 1. That's going to give me negative 1 over x. And then antiderivative for 1 over x plus 4.
ln x plus 4.
Got it. So there's the antiderivative. Hard part was breaking it down into those individual fractions. But that's one of the few techniques that actually solves this problem. That's what it's so excited saying.
I really like this stuff.
I do too. I think it's pretty cool.
I don't know which technique to use.
How do you know which technique to use? You try and see if it works, and if it doesn't work, you try another.
Is this what calculus people just do?
Yeah.
They just
They just sit around and
they just attack it with every
They just
single...
attack it with every tool possible. Yeah.
It's more fun when it's not.
Yeah, I have a blast writing test questions for you that are challenging yet doable. All right, let's do another one. So there was a request for, what, 12 or 14? Is that what I just heard? 12 is a butte.
I said 14.
14 is,
Nah, maybe we don't need to do 14.
14 is kind of sort of like what we just did. Let me see, where's 12? 12 is fun because we get to do long division. Yeah, let's do that one.
Yeah.
Who doesn't like to work with?
Okay. So now most of these problems give you a hint on how to do it, right? So without those hints, again, the general rule so either you're going to have a linear factor or you're going to have a quadratic factor. And there's a thing called the fundamental theorem of algebra, which pretty much says every single polynomial can be factored into linear and irreducible quadratic parts. Okay. So that's like a law of math. The hard part is finding those parts. Okay. So if you randomly made up a bunch of coefficients for like a 6th-degree polynomial, the chance that you could factor it in your lifetime is pretty small. But it is factorable. It's just the problems get hard once you get beyond like 4th or 5th power pretty fast. So if the factor is linear, that just means you're going to have something like a number over that linear factor. Let's call it mx plus b is a linear factor. If that linear factor has a power to it, then that just scales it up. So if it was something like mx plus b to the second power, then what you're going to have for your fraction decomposition is you'll have an a over mx plus b, mx plus b, and then you're going to have a b over the square of that. Why? Because there's a square here, mx plus b squared. Guess what would happen if there was a cube of a linear factor?
mx plus b.
Then you'd have an a, b, and a c with a mx plus b and mx plus b squared and mx plus b cubed. This goes on down the line like that. Similar thing for quadratic factors. If you have a quadratic factor, then your fraction is going to be something like ax plus b over whatever your quadratic factor was. Little ax squared plus little bx plus c. And guess what happens if that quadratic factor was squared? Well, it's the same rules as the linear factors, except you have these kinds of things in top. Those are the rules of partial fraction decomposition. So if you have a squared linear term, then you're going to have a couple things to deal with. If it was a cubed linear term, you'll have 3 things to deal with. If you have a single quadratic factor, then you have a single quadratic fraction to deal with. If you had a squared quadratic factor, then it would do something like that. Okay. All right, so back to this problem. So here, the other catch is, and I mentioned this the first day we went over this, is the degree of the numerator has to be smaller than the degree of the denominator in order for partial fraction decomposition to work. If the degree is bigger, you have to do long division to whittle it down. So that means we have to take x squared minus 1 into x cubed plus 3x squared. Why did they bother putting a 0x in there? Because you have to have that placeholder to do long division. Yeah. Could you use synthetic division on this?
You could factor the bottom.
Yes.
Oh, you could factor the bottom
And then
use
twice.
synthetic division twice. That is a pain in the butt. So pretty much you're better off using long division. So to do long division on this, I have to write this as x squared, and I'm going to put a 0x there too, minus 1. And whoa! I just freaked out. Again, that is. And that's going to go into 6x cubed plus 3x squared plus no x minus 3. So then you ask yourself, what would you multiply by x squared to get 6x cubed?
6x.
6x. So then we come up here, and I like to line up terms, so I'm going to put my 6x right there. And then I multiply by 6x by each of those, which is going to give me a 6x cubed. 6x times 0x is plus 0, x squared. And then 6x times minus 1 is minus 6x. And then you have to subtract, and the way to subtract is just add the opposite. So just take the opposite of each of these things and then add coming down. You're always going to eliminate one column at a time. So 6x cubed minus 6x cubed is no x cubes. 3x squared minus 0x squared is still 3x squared. And 0x plus 6x is plus 6x. And then bring down the next term. What would you multiply by x squared to get 3x squared?
Plus 3.
A 3 and it's a plus 3, yeah, correct. And then do your multiplication. And add the opposite. So,
We're still left with a plus 6x.
yep, that's okay. A new color, let's switch back to blue. There we go. So 3x squared minus 3x squared is 0. 6x minus 0x is 6x. Negative 3 plus 3 is 0. So this is my remainder right there. So that means this thing factors as 6x plus 3 plus a remainder of 6x out of x squared minus 1.
You need a remainder part?
Huh?
Is the remainder part important?
Is the remainder part important?
Well, yes.
Yeah. So for example, this problem is just a more complicated version of something like 2. Oops, that's not And 2 goes into 7 how many times? 3 times. 3 plus 2, 3 times 2 is 6, subtract to get a 1. Is that one remainder important?
Yes.
Yeah, it tells me that 7 halves is equal to 3 and 1/2. So I just turned this fraction into that mixed number. So just like I can take a fraction and turn it into a mixed number, that's what we're doing here. So a mixed number for a rational function is a polynomial plus another rational function. Right? It's analogous. Can we find an antiderivative for 6x plus 3? Heck yeah! That's way better than finding an antiderivative for that original thing. And then we can work on that second part right there. All right, so new page. We are at the point here where we need to find antiderivatives for this. So the 6x plus 3, that's easy. Any suggestions on what to do with the 6x over x squared minus 1? I have 2 options. Yes, Simon. Partial fraction decomposition is 1. Let's do that way because that's part of this section. What's the other way, Vitor? U substitution would work here too. Yeah, what would you let U be? The whole bottom. Yep, that would work here too. Let's do partial fractions next. So partial fraction says that 6x over, let's see, how does x squared minus 1 factor?
X minus 1, x plus 1.
X plus 1.
Yeah, so that's going to factor as a over x minus 1 plus b over x plus 1. Eliminate the common denominator, multiplying both sides by x minus 1 times x plus 1. And that's going to give me 6x equals, so the a over x minus 1 cancels with the x minus 1, giving me a times x plus 1. The x plus 1 under b cancels with the x plus 1, so I have b times x minus 1. And what are our convenient values here? And negative 1 and 1. So if x equals 1, I'll do that one first. I get 6 times 1 is 6, equals 1 plus 1 is 2a, and there's no b. So a is equal to 6 halves or 3. Then we do the same thing. The other clever factor or value is negative 1, because that makes 1 to 0. So then I get negative 6 equals negative 2b. And so b is also 3. All right, putting this all together, I've got the integral of 6x plus 3 over x minus 1 plus 3 over x plus 1 dx. And that's the other thing. Make sure you get your a and b in the right spot. Now here they're the same. That doesn't hurt. But when I mess this up, that's usually the place I mess up. Spot. All right, antiderivative. Let's see, 6x, that's going to be
3x squared.
Over 2, yeah, so 3x squared plus 3x plus 3 times
ln x minus 1.
ln, just absolute value, x minus 1 plus 3 times the ln of absolute value of x plus 1 plus c. Will we get the same answer for U substitution?
Yes.
No.
No.
Not necessarily. Why not?
Because we didn't have because to different. We don't have natural
different constant.
Yeah, it could be a different constant that's involved.
We only have one natural law.
If we do it the other way?
Yeah.
Oh yeah, let's do it just for fun. Okay.
Just had to ask.
So, so just consider this part right here, what was it, 6x over x squared minus 1?
Yeah.
So if I was just going to do a u substitution here, u I would let be the whole x squared minus 1. Du would then be 2x dx. And I have some of that up there. If I consider that 6 is 3 times 2. So when I substitute in here, I'm going to pull out that 3, because this part then is my du. So I have 1 over u du.
So then you just get a single natural log.
So now I get 3 times the natural log of the absolute value of u, but u is really
X squared minus 1.
x squared minus 1. But x squared minus 1, what is that equal to?
X minus 1, x plus 1.
It's equal to, yeah, so this is really 3 times absolute value, natural log of the absolute value of x minus 1 times x plus 1.
And you can split them up.
And logarithms can split on a product to become the sum of the logs. So this is the same thing as 3 times the natural log of x minus 1 plus 3 times the natural log of x plus 1, which, although it looked different at first, a little algebra shows it's actually the same thing we already found.
Worst case scenario.
So sometimes it's, so what's that?
That seemed way easier.
You don't know till you try both ways is the problem. You know? So you just throw a tool at it, hope it works. If it doesn't work or you're not sure, try another tool. Yep.
Then with the absolute values for the natural logs, and it counted it as wrong.
It didn't like the absolute values in there?
No, it did. I did.
You did it and it counted them as right?
Parentheses inside your absolute values, otherwise it's a syntax error.
No, the syntax is the syntax is okay.
Okay.
It says
So let me. So for this one,
for
I
mine-
have a 6,
For mine, it for the
3.
answer, it says that it doesn't want the value.
Those are my constants, right? 6, 3, 3, and 3.
Sometimes
Okay.
they just like,
So then I thought the answer was 3x squared plus 3x plus, let's see if it accepts that other one, 3 times the natural log of the absolute value of x squared minus 1.
you know,
I think
I
so.
don't know. I don't think it
It doesn't
does.
It doesn't take them?
You have to write ABS.
I can't, I'm in print mode, I can't see the answer. Darn. It wants me to use ABS,
Yeah.
so I would have to do parentheses. I think it accepts those bars, it doesn't?
And then another.
And then
So I have parentheses and then absolute value parentheses x squared minus 1, close.
When you use the pad,
syntax.
you'll actually
Yeah.
get an absolute value.
They use ABS.
No, you get an absolute value box option.
Okay, let's see what that looks like. Can I get that here?
Well, it's when you're in regular mode,
It's
you
off
get
the
the
screen.
little yellow box on the side. And
Let's
you go
see.
to full
You
pad.
can't do it because you're print mode.
Yeah.
Ah, I'm in
Doesn't
print
give you
mode.
Control A, Control V.
Oh wait, it's over here though. Which number was this? 12? Is that the same
Did
one?
we get luck?
Yes.
Yes.
Yeah, okay.
Everybody.
All right, so
Copy
the
paste
it.
screen
Copy
is too
paste it.
big. What
So we
happens
add
if I do that?
3x plus 3.
It enters as ABS, okay. I'm curious if I can enter it the other way, so let's see. 3x
Gary, you
squared
can copy
plus,
paste it.
That was
oh, I could have copied and pasted it.
Good old Control C.
Where'd it go?
Control V.
I've used ABS before.
you did a cube instead of squared.
So have I heard that this now? Like,
You? I know.
Oh, it took it.
It took it, okay, does it accept those bars?
I don't even know how to make those stupid little bars on mine.
It's on the keyboard.
It shifts, it's above enter on the right.
underneath.
Oh, there it is. Okay.
Yeah, the syntax
Oh, the
error.
syntax error?
No, it's because of the
It's
bars.
inside the bars.
Oh yeah, probably wants parentheses with the natural log because it's a function.
Oh,
So that.
Yep,
Took it.
still likes it.
How
Okay.
weird.
Yeah. All right, cool.
we've been.
Let's see, we are running out of time. So you have to do clever algebra. So I'm going to go back to section 3. Be a problem from there. And again, section 5 is
You
just.
just closed it.
I did?
3:30.
Yeah, 3.
Thank you. All right, what looks cute here? I'm going to scroll to the print version. 12 looks cute.
So I think it's
We just did 12.
Oh, this is a
No,
different
it's
section.
good.
Oh.
Um,
Oh, that one was
Oh
fun.
yeah, let's do this one. That
The
looks
first
awesome.
time I did it, I kept typing in the integral, and I was like, "Why isn't this working?" And it's because it wanted you to find the whole area, not the integral.
Okay.
It was interesting.
Flashbacks.
I know.
Okay. So just a reminder about an ellipse in your past life in math. The equation for an ellipse looks something like this one, where you have x squared over, let's call it a squared, plus y squared over some number b squared equals 1. And then the ellipse you get will be centered at the origin if it's just an x squared and a y squared. And the a is in this case, if a is bigger than b, we would call that the major axis. So I would have a point over here at negative a0 and another point over here at a0. And the b would be the semi-major axis, which would give me a point 0, negative 0b up here, excuse me, and 0, negative b down there.
So if B is greater than A, does that mean that the major axis flips or is
Yeah.
regardless still?
It just flips it. Yeah. So again, an ellipse could look more circular if a and b are closer together in value, and this one it could be sideways wide or long ways tall. There's a lot of different things. So in this case, I would consider this is x squared over 6 squared plus y squared over 4 squared. So that means this thing goes from negative 6 to 6 on the x direction and 4 to negative 4 in the y direction. And we were asked to find the area, right?
Mm-hmm.
So one thing I can do with an ellipse is I can use symmetry and just do that region right there and multiply by 4. Okay. So in which case I would want to solve this for y. So I'm going to get y equals some function of x for this curve. And then I can just integrate from 0 to a and multiply by 4. So if I solve this for y, what am I going to get? I'll have a 1 minus x squared over 36.
Oh, because Y equals over.
And then I need to multiply that by 16. And then take the square roots plus or minus. Right, so I'd have to subtract this term over, I'd have to multiply by 16, and then I have to take the square root. So cleaning up that a little bit, and I'm just going to worry about the positive, which would be this whole top right there. And I'm just going to use part of it. So square root of 16 as a multiple is nice, because that's going to pop out. So I'm going to get y equals 4 times the square root of 1 minus x squared over 36. Is going to be my function. And we want to integrate that from 0 to 6. All right, so I'm going to write that down, and then we'll apply quick substitution to that. So I want 4 times the integral as x goes from 0 to 6 of 4 times the square root of, that's supposed to be 1, oops, 1 minus x squared over 36 dx. Is anyone unhappy with that divide by 36 there? Or can you live with it? It's fine. Okay. Because we could factor it out.
We're gonna leave it.
So triangle time. So since I have a minus in there, that is not the hypotenuse. So there's theta. The hypotenuse must be the 1 because I'm subtracting from it. And then that x squared over 36 is really the square of x over 6. So then I want x over 6 to be this side right there. Well, the square root would then be this side right there. 1 minus x over 6 squared. So there's my triangle. On this triangle here, the easiest ratio to work with is the opposite over the hypotenuse, which means sine. This is what's going on in this one right here. So I get that the sine of theta is equal to x over 6 divided by 1, which is just x over 6. And we could bring that 6 over to the other side. So I could say this is x equals 6 sine of theta. Dx would then be what?
6 cosine.
6 cosine d theta. And what's the square root here?
Cosine.
It is cosine,
Yeah.
because cosine is adjacent over hypotenuse. And so the square root of 1 minus x over 6 squared oops, is equal to just the cosine of theta. Because again, cosine is adjacent to the hypotenuse. So let's see, what do I have in my integrand? Well, my integrand has a square root, so that means I'm going to need a cosine. And my integrand has a dx, so I'm going to need a 6 cosine. Otherwise, we have those two 4's hanging out. I'm going to redraw this in, let's say, blue. So I'm going to pull out 4 times 4. Oops, that's not a pen. Thank you. So I have a 4, I have a 4. I'm going to get a 6 over here, so I'm going to pull that out now too. And then otherwise I have cosine times cosine, which is cosine squared of theta d theta. And what do we do with the cosine squared? We use the double angle, half angle, depending on your perspective. So new page, I've got 4 times 6 chilling out. I don't want to multiply those out if you don't mind. And then the cosine squared is 1/2 times parentheses 1 plus the cosine of 2 theta. Hopefully you're getting used to that identity. Cleaning up constants a little more. Half of one of those 4's gives me 2 times 4 times 6 as my constants. Okay, so theta is my variable. What's the antiderivative of 1?
Theta.
Right, it's just theta. And antiderivative for cosine?
1/2 cosine.
Yeah, because
There's
it's a 2,
negative sign.
I'm going to need a 1/2. Otherwise, it is the sine of 2 theta. Double check, what's the derivative of sine of 2 theta? It would be 2 times the cosine of 2 theta. The 2 kills that 1/2 I have to throw in. Next fun part, reverse substitute. So to reverse substitute here, I have 2 slight problems. One, theta does not sit all by itself over here. But I could pull it out of this equation, couldn't I? Yeah, so according to that, theta is the arc sine of x over 6. Other consideration is I have sine of theta sitting here, but I do not have the sine of 2 theta. So we have to use an identity on the sine of 2 theta in order to use reverse substitute. Does anybody recall the double angle sine? It's twice the sine of theta times the cosine of theta.
Okay.
So, let's see, my 2 times 4 times 6 is still chilling out, parentheses. That theta right there is an arc sine of x over 6. Then I have plus 1/2. The sine of 2 theta is twice the sine of theta times the cosine of theta. So I temporarily have mixed variables. We'll get rid of that in just a second. What do we believe the sine of theta to be equal to? According to our triangle, x over 6, and the cosine is that square root. So putting it all together, let's see, I might as well deal with the 6 times 2 times 4, what's that, 48?
Should I have time here?
No,
We're out of time.
I know, I'll
Okay.
keep going. I'm almost done. So I have 48 times the arc sine of x over 6. Well, 2 times 1/2, that's nice, it's gone. The sine of x is x over 6, right? And the cosine of x is our original square root. 1 minus x squared over 36. Let's see. Whew, that's a workout.
Did that get your heart rate up?
That did get my heart rate up.
And then you have to-
I feel like it just spiked up.
And then you have
Then you
to,
have to,
Oh, I gotta evaluate this from 0, oh darn, there is no
0 to
plus
6.
c. We have to evaluate this from 0 to 6. All right,
So it's
good luck on your homework.
Like in decimals.
Thanks.
Yeah, and again, don't consider plugging in 0, 0 stuff out. Sometimes it does, sometimes it doesn't. You gotta check. We're out of time for fun with math, my apologies. There's not enough time in the day for all this beautiful math.
Yeah. I'll see you next week here.
You will.